Just to summarize where we are. So in a simple compiler with only a front end and back end, it is with only a front end and in a simple compiler with only a simple and back with the front end and the back end, what happens is the quality of code that gets generated, it will not be good. The program can take a lot more time to execute. So in order to optimize the program and in order to generate better quality code, in order to generate better quality code, the generated IR is multiple machine-independent optimizations will be applied on the generated IR. And we will see what these machine-independent optimizations are at a high level in today's session. So if you look at the optimizer module of a compiler, so it consists of a series of analysis and transformation passes. There will be, in order to do certain kind of transformation on the intermediate representation, you have to do certain kind of program analysis. So what happens is, so you will have a certain analysis module, and then followed by that, a transformation module will be invoked, and then again some other analysis module, and followed by that, the corresponding transformation module will be invoked. It keeps going like that. So your compiler, the middle end of your compiler, makes multiple passes on the intermediate representation, and these passes are either analysis passes or transformation passes. And finally, a optimized intermediate representation will be passed to the middle end. One important thing which I didn't highlight here in this slide is, if you see, you can, so the optimizations, there are two kinds of optimizations that are possible. One kind of optimizations, they are called as machine-independent optimizations. And after machine-independent optimizations are done, code generation will be done, and then target machine-dependent optimizations will also be performed. So by and large, we will be seeing only machine-independent optimizations in this course. And maybe one or two machine-dependent optimizations also we may see later on. So example machine, there are again in these machine independent optimizations, there are many are possible. So let's say if you consider a couple of categories. So one category of machine independent optimizations, they try to eliminate redundant computations. Like for example, when you are trying to compute in a loop, so you have a loop, you have a while loop, okay, and in the while loop you are computing the area of a circle, which is something like 2 pi r, and then you have somewhere up here hash define pi is equal to 3.14 or something. So you can see, so this 2 pi will be computed again and again through multiple iterations of the while statement. And what happens is, so it's a redundant computation. You know the value of 2 times pi, so we might as well move this 2 times pi outside this while loop and use its value. You can kind of transform this code into by saying t is equal to 2 star pi, and then you can replace this 2 star pi with t here, and it's good. Or you can actually, it's 2 star pi, it's a constant. So instead of putting it in a variable, you can actually replace this 2 star pi with the constant 6.28. And this could also be useful in generating good code, because you can keep this constant in some register and not and move that value from the memory to a register and do the computation. It's a constant. You keep this constant in some register and generate code which does the computation directly by working on it. So like that, many interesting optimizations the compiler can do in order to optimize the code. So this is this is an example. So what we did right now, so this is an example of move loop invariant computations out of the loop. Great. And then avoiding superfluous computations. There are some kinds of optimizations which try to avoid superfluous computations. So anyway, we try to look at, understand what these optimizations are by looking at a few examples. So let's look at, like in C, when you access, so in C, when you, in array access such as A of I comma j, so I think in C, it will be something like A of ij. This is how you will be doing an array access in C programming language. In Algol programming language, maybe you will be using A of I comma j in this particular form. But in any case, what happens is this gets transformed, this particular array access gets transformed into an expression such as this. So what is the address of the element A of ij? So to the base address, you multiply I times, you add this offset. This is the whole offset. So this I star m plus 1, it tells the number of rows to skip. Like for example, if I is equal to 0, then we don't need to skip any rows. So you have to go to the jth position in row 0. So jth position in row 0 is what you have to go through if I is equal to 0. But on the contrary, if I is equal to 1, then, so since this whole two-dimensional array is mapped to a linear array, so you have to skip the first m plus 1 elements and then go and access the next row. So a array access such as A of I comma j, it will be mapped internally, it will be mapped to an expression like this. So this gives the address, and CONT means the content of the corresponding memory location. It gets mapped to something like this. So if you see from the C program, when you just look at the C program, you don't see an array access doesn't look like involve any computations. It just looks like a memory access operation. But if you take, once that array abstraction is lowered down, then you will see it generates, like there is a multiplication operation it generated, and couple of addition operations are also generated as a part of this. So what looks like a mere memory access operation, but when the abstraction gets lowered, you will see certain computations are being exposed to the compiler. So let's take this simple program. So in this program, this is a program to add a sum of two arrays and two matrices. So you add matrix B and matrix C and store it in matrix A. And you can see how this code gets mapped internally to when it gets lowered down. So you will see the address of the array element A of ij is computed on this line. Okay, so address of the array element. So temp contains the address of the array element A of ij. So content of temp is equal to content of the memory location associated with Bij. So this corresponds to B of ij, and this corresponds to C of ij. So this is how our basic matrix addition algorithm, if you lower it a little bit, this is how it looks like. And you can see here multiple redundant computations in this after it gets lowered down. Yeah. So if you look at this code, so this I star m plus 1, I star, so the whole subexpression here, it is being, we are doing this computation. This is the first time we are computing. This is the second time we are computing, and this is the third time we are computing. So the second and third computations, they are recomputations of the same expression. But if you look at the source code level, these recomputations are not exposed to us. Only after you lower the source code a bit to a form which is closer to the machine, then these recomputations are exposed. So how can we eliminate these recomputations? So the value, the first computation value, you store it in a temporary variable T1. Okay, this is what is called as a temporary variable. During the process of IR generation and during the process of code generation, the compiler uses lots of temporary variables which are not visible to the end user. So the end user only looks at the variables he or she declared, but internally compiler can generate a lot of temporary variables which it can use. So the value of the first computation is stored in the temporary variable T1, and temp is equal to, and then what happens is in the second and third computation, so instead of recomputing, we use the value that is computed already there. So this is the code. This block of code here, it will be transformed into this. So here you can see we do what is called as an available expressions analysis. This is an analysis pass, available expressions. This is an analysis pass. So in order to identify that we know this whole sub-expression is being recomputed, so we do available expressions analysis pass. And then once we identify these available expressions, and what we do is we do a transformation pass. The transformation pass is called as common sub-expression elimination. So there is an analysis pass and there is a transformation pass. So the analysis pass finds redundant computations and the transformation pass eliminates the redundant computations. So now let's see the transformed code. So what you are seeing on the left is a transformed code. And then if you see this inner loop, in this inner loop, this I star m plus 1, this sub-expression value, it remains the same in the inner loop, because in the inner loop only j is changing, but I is not changing. So the sub-expression I star m plus 1, this is loop invariant. So what we can do is we can move this loop, this computation, which doesn't change across loop iterations, out of the loop. So this is what we do. This is the transformed code. This whole block gets transformed to this particular fashion. So T2 is equal to, now again we use a new temporary variable called as T2. In T2, we say T2 is equal to I star m plus 1. So this statement gets transformed to this statement. T1 is equal to T2 plus j. So again, here there's an analysis pass. The analysis pass is detection of loop invariant expressions, and the transformation pass is invariant code motion. So one more compiler analysis and transformation pass. Here you can see in the outer loop, T2 is equal to I star m plus 1. But if you see the value of T2, initially it is equal to 0. When I is equal to 0, T2 is equal to 0. When I is equal to, so if you see, so you know I is equal to 0, 1, 2, 3, 4, like that it goes. And if you look at the variable T2, the variable T2 will see something like it is equal to 0, m plus 1, 2 times m plus 1, and 3 times m plus 1, like that it goes. And you can see the difference between the value of T2 across 2 iterations. If you see, it always increases by m plus 1. So what we do is, multiplication operation is much more expensive than addition operation, especially in older machines, let's say machines which are processors which are 20 years old, or in earlier processors that were designed, multiplication is definitely more expensive than addition. So what we do is we eliminate a multiplication operation and we introduce a addition operation. So this is the transformed code. So if you see in the transformed code, so we introduced an induction variable T3, and this T3 variable, it keeps getting incremented by m plus 1. So this is what is called as detection of induction variables analysis pass. Detection of induction variables analysis pass. And then followed by that, we do a transformation pass, which is called as reduction of strength transformation. And what you are seeing on the right-hand side is the transformed code. And you can see the multiplication operation is eliminated, and a addition operation is being introduced. And this whole while loop, it is kind of summarized in this small box, because we are not touching the while loop in this. The code transformations are happening in the outer while loop, but not in the inner while loop. So it is just, it just remains as it is. So one important thing here is this T2 is equal to I star m plus 1. It got transformed into T2 is equal to T3. And at the end of the while loop, T3 gets incremented by a value m plus 1. And T3 is initialized to 0 in order to take care of the loop initialization. When we enter the loop for the first time, T3 should have a valid value. This is how the whole analysis and transformation occurs here. So now one more analysis and transformation pass. So here you have this T2 is equal to T3. And if you look at the inner loop, we are using the value of T2. So we are just copying the value. There is one memory access. So here, and nothing is happening here. So you copy T3 to T2, and then you use T2. So that's all. And you can as well see, and this kind of invokes one memory write and one memory read. Memory write to T2 and memory read from T2. So here you have a write, memwrite, and here you have a memread. And what we can do is we can, instead of using T2 here, we may just replace this T2 with T3, and so the transformed code looks like this. And the analysis pass here is what is called as an equivalent expressions analysis pass. And the optimization that we perform is what is called as a copy propagation optimization or copy propagation transformation. So the code that is there on the left-hand side, now it got transformed to the code that you're seeing on the right-hand side. So now, great. So let's move on. Now you can see at the end of all this analysis and transformation passes, this particular statement, if you look at this particular statement, we are doing an assignment to the variable T2, but the variable T2 is not used anywhere. So there is a definition for variable T2, but there is no use for the variable T2. So we can say that the variable T2 is not live. And there is an analysis pass called as live variable analysis pass, which will figure out at different points in the program what are all the variables that are live. And if at a particular point in the program, if a variable is not live, but it is still being defined, then the corresponding statement is dead code because it doesn't serve any purpose. So here, what it means is this whole assignment statement, it is a dead code because the variable T2 is not live in this program after this point. There is no use for the variable T2 after this definition point. So after doing live variable analysis, we will successfully determine that this is a dead code, and we do a transformation pass called as dead code elimination. So after we do the dead code elimination, you can see that finally the code got transformed. Great. So you can see this is the whole. So we started with some code base and we applied a series of analysis and transformation passes to finally arrive at an optimized IR. And in this particular example, you can see it is possible for us to do most of this analysis and transformation passes at a high level. But there are some other on high level code, but there are many analysis and transformation passes which can be applied only at the low level, on low level IR. Not only that, during the process of lowering the IR from higher level abstractions to lower level abstractions, more and more inefficiencies in the generated code you will see. So right now, there could be some inefficiencies that may crop up when we map these while loops, etc., into lower level IR, but they are not visible yet here because those abstractions are not yet lowered down to a different IR. The summary of all the things that we have seen is there is a series of, on the source code, we applied a series of analysis passes. So initially we applied available expressions analysis pass, and then the associated transformation pass is called as common sub-expression elimination. And then we have detection of loop invariance analysis pass, and the associated pass is invariant code motion. And then we have detection of induction variables analysis pass. The associated transformation pass is strength reduction. Similarly, we have equivalent expressions analysis pass, and the associated transformation pass is copy propagation. And finally, we did live variable analysis and the associated transformation passes dead code elimination. So it's important that if we just apply this, any of these transformation passes without doing the associated or the corresponding analysis passes, these transformation passes are useless. First of all, in compilers, so when you invoke a common sub-expression elimination transformation pass, this analysis pass is the corresponding analysis pass is automatically invoked, because in the absence of that analysis pass, the necessary information to do the transformation will not be present at all. So the analysis pass is useless. So if you, like for example, in LLVM, if you kind of invoke loop invariant code motion optimization pass, I would presume it will automatically invoke the corresponding analysis pass, because without an analysis pass, no information is available for the transformation pass to take suitable actions. So this is the most important thing about program analysis, which we will be studying in the next few lectures. That is, see, program analysis offers techniques for predicting statically at compile time safe and efficient approximations. So all the analysis passes that we are doing them at the compile time. So this is what is called as static program analysis techniques. Static program analysis techniques. So these are all static program analysis techniques. And when we do these analysis techniques, when we do static program analysis techniques, what happens is, when you run the program can take different execution paths and execution behaviors, the program, depending upon the input and some other external stimuli. The program can take different execution paths. And the conclusions that we make about the program behavior at the time of compilation, they have to be valid across all execution paths which the program takes. And here, so we kind of do what are called as safe approximations. And these safe approximations, they facilitate transformations which doesn't change the semantics of the program. So if you do an approximation and which is not safe, and based on that you do a transformation, and that transformation could change the semantics of the program, then the program is no good use. If you're going to change the semantics of the program, then forget about it. So it's not going to work. All right. And we will try to understand about these safe approximations through multiple examples as we progress through the next few lectures. So in order to kind of get some kind of intuition, if you see, let's say these are so whatever you are seeing here, this is a set of behaviors or execution paths which your program can take. But we don't have these execution paths available in our hand, because number one, they are infinitely many. Number two, these execution paths, in order to uncover them or discover them, you have to provide suitable input in order to figure out all these execution paths. So we have to do an approximation of these execution paths. Sometimes we do over approximation, and sometimes we do under approximation. In some cases, over approximation is better, and in some other cases, under approximation is better. So whether we do over approximation or under approximation, it depends on what kind of transformation paths that we are trying to apply. Like for example, when we are doing this live variable analysis, and if we conclude that a variable is not live, while it could be live, that is an under approximation, in which case we will end up doing dead code elimination in an incorrect way, leading to violation of the program semantics. So when we are doing live variable analysis, we may want to say that a variable is live while it is not live. Okay, like for example, in this particular case, let's go back to the example. Yeah. So in this example, if we kind of say that the variable, if we do an over approximation, what is an over approximation? You say that a variable T2 is live while it is not live. So here, in this case, if you do over approximation, if you do over approximation, so it is all right. It is all right because you lose an optimization opportunity, but you are not going to violate the semantics of the program. But on the contrary, if you kind of do an under approximation, like for example, you say the variable j is live, but you say it is not live. Okay, it's an under approximation. Then what happens is you think that the transformation pass thinks that this is a dead statement and it eliminates it. So when you do under approximation, so in the case of live variable analysis, and the dead code elimination transformation paths put together, over approximation is good. Over approximation is all right, no problem, is all right. You lose an optimization opportunity, but under approximation, you should not do it. Because it violates the program semantics. And there could be some other cases where under approximation is better, but over approximation is bad. So depending upon the transformation paths that we are trying to apply, so whether we want to do over approximation or under approximation, we have to decide. But the key thing is, the whole goal is when you are designing these analysis and transformation passes, the program semantics has to be, cannot be violated, because then the whole purpose of this optimization gets lost. And here, so this is whether it is over or under approximation. So we can call it as safe approximation. You have to do what is called as a safe approximation. So in some cases, safe approximation could mean over approximation. In some other cases, it could mean under approximation. But safe approximation is what we have to do. And there is a second idea. So later on, you will see, if you want to improve the precision, like for example, let's say even if you decide to do over approximation and it is a safe approximation to do, we want this circle to be as close to this exact configuration. And let's say if it takes, there are two algorithms for you. One algorithm has exponential time complexity, but the solution given is very close to this exact configuration. But the other algorithm is a polynomial time algorithm, but its precision is slightly less. So you may want to consider taking the polynomial time algorithm for approximation rather than exponential time for the computing this safe approximation. You may lose some precision in the process, but if the loss of precision is not much, then there is no point in increasing the compile time of the program. Yesterday we have seen when in the lab, when we did a make of this, this small software module, it took quite some time. So if you end up spending using exponential time algorithms, for example, in our compilers, in the compiler, then the compilation time just shoots up, and so it would not be a viable option to use in practice. There are some cases where you may want to consider exponential time uh, uh, analysis algorithms. Like for example, I work in compilers which take high level code and map them into target architectures, which can be transformed into ASICs or FPG or put on FPGAs. In that area where you are generating hardware, so once an ASIC is generated, this ASIC, once a design is generated and you kind of put it into an ASIC, this ASIC may last for, few years. So, and you may want to put in a lot more time in order to generate an optimal hardware design. So there possibly you may or fine with using a slightly higher complexity algorithms. But then there is a cost to pay because, like even for small designs, when we do what is called as a synthesis, it takes few hours to synthesize the design. Yeah, it's an expensive process. The whole development process is expensive because you have a design and you do a small change and in the design, and then you want to synthesize the design, and this synthesis of the design takes 6 hours, and you don't have anything else to do, and the productivity comes down substantially, and it's a very very expensive process. So you really have to see whether the cost that we are putting in the compile time by using algorithms or optimization algorithms whose time complexity is higher is really worth it. Okay, so that is where this trading precision for efficiency comes into picture. So that is all I have for today. Now we'll conclude this lecture here. If you have any questions, you can ask me now.